we'll build off of there. So what you already know is you know what a discrete PDF looks like, okay? You are familiar with this construction of a PDF where x can be, some number of values, 1, 2, or 3, and if it's one of those values, it has some distribution like 0.3, 0.6, 0.1, that's the probability x is each of those things, right? That looks familiar to all of you from your last exam, okay? Well, in continuous land, over here, we're not talking about something discrete, we're talking about continuous. Instead, your PDF is going to follow some distribution where if x is exists in some interval between, let's say, let's make it interesting. So x is going to be between 1 and 3, right? So if x is in that interval, then it's actually going to be some type of function, right? Let's say, just randomly, that function is negative 3/10, let's see, x, what is this random function? X squared minus 4x plus 2, okay? So that's what that function is going to be if x is in these bounds, and if x is not in those bounds, then f of x is going to be 0, right? So we've constructed a continuous PDF, right? The difference is that here x can only be 1, 2, or 3. Here x can be an infinite number of things between 1 and 3. Okay? So if I were to graph this, then I would have 1, I would have 3, and let's say I graphed this and I got, I think it peaks out at like 3/5 or whatever. So if I graphed this, I would have something that looks kind of like that. Okay? Yeah. So is this the same thing as this?
No.
No, why?
It's not. The balance is 3. Yeah.
Right. I didn't get my bounds 1 to 3. So in reality, it actually looks, more like that. All right? That's my PDF right there. Okay? And the area under this curve is going to equal what? 1. Okay? That is what makes it a valid PDF. That entire area is going to be 1. Okay? So if I had some function that integrated over this entire PDF, because that's the only way that I can talk about probabilities here. If I were to ask the probability that x is exactly 2.176, then what's the probability that x is exactly that? 0. Yeah, I mean, x can be an infinite number of things. If I'm asking if x can be one specific thing in that infinite range, that probability is basically 0, right? So instead, we talk about ranges of probabilities, and we get those by integrating and finding the area under that curve. Okay, so if I were to draw some function that showed my journey of integrating over this, then first of all, going from negative infinity to 1, then what would that function be? It would be 0, right? Negative infinity to 1, it would be 0, and then I would start integrating, and I would start capturing. These slices are getting bigger and bigger in this function, so I imagine it would kind of get some traction up here, and then I'm getting like smaller and smaller slices, so then it would start to level out. So for this example, that journey would look kind of like this, and then it would top out at 1, and then it would just be 1 forever. Okay, so this accumulates this entire function. So let's call it a cumulative distribution function, or a CDF. All right, cool, like that. So if I were to take the CDF, it is you see that entire function is the integral of the PDF. All right, so it would look something like this. If x is in the interval 1 to 3, then well, let's just find it right now. Okay, somebody integrate this. What's it turn into?
Negative 3 over 10 will be just the coefficient.
All right, leave the negative 3/10. It's on the inside.
And then it will be x cubed over 3.
X cubed over 3
minus x squared 2, which would be 2x squared.
2x squared over 2.
I like it. Okay, x cubed over 3 minus 2x squared.
All these plus 2x.
Plus 2x. Hey!
Knowledge vibes coming in.
So much knowledge. Okay, so if I just integrated that, is just integrating that going to give me my CDF? The indefinite integral, just plugging it right in here, is that my CDF? No, because, yeah, I have to do it considering these bounds right here. Well, specifically, I'm doing to x, so 3 it doesn't actually matter. But yes, I have to consider this 1. So I'm going to subtract, I'm integrating my PDF, squared minus 4x plus 2. I'm integrating that all the way from x's lowest bound, which is the same thing as negative infinity. You just got to remember to subtract this lowest bound. I like to write the lowest bound all the way to x. Okay, and as we said, we're going to get negative 3/10 x cubed over 3 minus 2x squared plus 2x evaluated at 1, 2x. Well, if we plug in x, then it's just going to look like that, right? But if we plug in 1, what's this going to turn into? 1/3 times negative 3/10 gives us
1/10.
1/10, right? So it's actually just going to be this minus, is that minus 1/10 or plus 1/10? Minus negative 1/10 is plus 1/10. Yep, okay, so this is what my CDF would look like. If x is in the bounds 1 to 3, it would be negative 3/10 x cubed over 3 minus 4x squared plus 2 plus 1/10. Otherwise,
2x.
did I mess it up? Oh, my bad.
No, the other one.
Oh, 2x. Now I'm done? Okay. So, if x is less than the lowest bound, what's it going to be? 0. And if it's more than the highest bound, what's it going to be? 1. Okay. 0, 1. Okay. So, how do we check if this is a valid CDF? Right. Those are great ideas that would take way too long. My idea is I'm going to plug in the highest bound, and I should get 1. And if I plug in the lowest bound, I should get 0. So if I plug in 3 here, I get 27 over 3 is 9 minus 18. 9 minus 18 is negative 9 plus 6 is negative 3.
What is that?
That's plus 1/10.
Just plus 1/10 is all.
Yeah.
That's plus 2x.
That's 2x. Sorry, I was running into my CDF right here. That's my bad. Plus 2x plus 1/10.
Okay.
Okay. So, yes. So anyway, what did we get here? We got 3.
I think we're negative 3 on the inside.
Yeah, I think it was just 3, right? Or negative 3? Negative 3 times negative 3/10 is 9/10 plus 1/10 is 1. Perfect. And if we plugged in 0, or we've plugged in 1, we get 1/3 minus 2 plus 2. 1/3 times negative 3/10 is negative 1/10 plus 1/10 is 0. Everyone follow how to get a valid CDF, how to check if it's valid. Okay, so will you ever submit a CDF that is not valid?
Only for silly.
Okay, I will accept it. Okay, so that is PDF, CDF logic right there. Any questions on that? Okay, we all know that pretty well. That's great. Now, the percent. So if I were to shade some area under this, and this area were 0.2, that would be, this number right here would be the 20th percentile of this function. Okay, if I were to shade some area under this and it were 0.9, then whatever that value is would be the 90th percentile of this function. The same thing as saying, oh, right here it's 0.2, right here it's 0.9, right? Whatever these values are my percentiles. That's what percentiles are. Okay, what would be the median of the function? What percentile would that be? 50th percentile, right? So if you're ever asked for the median, that is the 50th percentile of your function, right there. Okay, that's your median. Sometimes, if you have a symmetric function like this one, it'll probably be the same as your mean. If your function isn't symmetric, your mean and median will be different. Okay, so yes, that is percentiles. Now, we are going to move into, you guys cool if I erase this all? Okay, we're going to move into some other stuff. So here's some other stuff that you're familiar with. You're familiar with joint PDFs, right? So in discrete land, you could write it out, but I'll actually write it as a table because I like that better. So joint PDFs, you might have some, X is up here, it could be 1, 2, or 3. Y could be some number of values, 10 or 20, and you have some distribution of probabilities, like that, yeah, okay, right? So you have some distribution of probabilities up here, and that is a joint PDF in discrete land, right? If you wanted the marginal distribution of y, you would sum over all of these x's, and by summing over all of the x's, you would eliminate x and get just a marginal distribution of y. That would be, when y is 10, it would be 0.65, when y is 20, it would be 0.35, okay? That's a marginal distribution. And if you wanted a conditional distribution, let's say you wanted the distribution of y when x equals 3, then you would take these numbers and you would apply Bayes' rule, which is probability of A given B is intersect B over probability of B. The great Bayes' rule, which is basically all this class is. Okay, so you would take Bayes' rule, you would take the intersect, take it over the probability that x is 3, okay? And so you take 0.05 over 0.25, which is 1/5, and when y is 20, 0.2 over 0.25 would be 4/5, okay? That's something you guys have all done. You've all done these distributions all the same way before. Now in continuous land, we're going to continue doing these, but a marginal distribution is going to be, a joint distribution is going to be something like this. If x is in some bounds, I'm going to make this a really simple one, and y is in some bounds. I'm just going to make them both between 0 and 1, but these can be different. And we'll say that your function is negative x minus y plus 2. Okay? And if either of those are not true, then your function is just going to be 0. Okay? So that is your joint distribution. So if you wanted the Cdf of this joint distribution, then you would apply exactly the same thing that we've been doing. You would integrate over it, except this is a 2-variable equation, so you would take the double integral, and inside it, you could do it in terms of x first or y second, or flip them, it doesn't matter, but basically you take the bounds of x, a to b, and take it in terms of dx, it's y plus 2, and then you take the bounds for y, dy, and by integrating over, I'm so sorry, we'd actually do that, 2x and 2y, and by integrating over this whole thing, you would then get a joint PDF in terms of x and y. Okay, do this. What do you guys get? Let's do dx first. What's it turn into?
Okay, x squared, or negative x squared minus x.
minus yx plus 2x. Okay, now let's do it in terms of y. What do we get?
Negative x squared over 2y.
Okay, okay, perfect. Plus 2xy. Okay,
Do
this.
we not have to plug in x and the lower bound?
Yes, sorry.
He did.
Yes,
Oh,
we are
it's
shortcutting
zero.
it. You would plug this in, you would evaluate this at the bounds of x from 0 to x. Because our lowest bound is 0, we're not doing that.
Okay.
But then you would, from 0 to y, yes, you are correct. Make sure to do that. But we get this as our CDF. Does that look like a valid CDF?
Yeah.
If we plug in our highest bounds, 1, we'll get negative 1/2 minus 1/2 plus 2 equals 1. Okay, great. If we plug in the lowest bound, 0, we'll get 0 minus 0 plus 0 is 0. I like it. It looks like a valid CDF. Okay. Now, if we wanted a marginal distribution, then just like this, we summed over all of our x's. By doing so, we eliminated x, and we got a marginal distribution for y. So we'll do the same thing. If we want a marginal distribution for y, we will sum or integrate over all of our x's. And this time we will use every bound of x. And we're going to do that for our entire function, integrating over all of our x's. And let's see if that gets rid of x. So that's going to be negative x squared over 2 minus xy plus 2x evaluated at 0 to 1, which gives negative 1/2 minus y plus 2 is 3/2 minus y. Okay, so that is your marginal distribution for y. All right. If I wanted a conditional distribution, just like in discrete land, I would apply to Bayes' rule. And in continuous land, what Bayes' rule means here would be that, let's say I wanted the distribution of x when y is 3/4. Okay, so in order to get that, then according to Bayes' rule, that would be the joint distribution plugging in x and y is 3/4 over marginal distribution of y when y is 3/4. Okay, by plugging in that, I should get this right here. So let's go ahead and do that. My joint distribution, I plug in x, I plug in 3/4 for y. I got negative x minus 3/4 plus 2 is negative x plus 5/4, I think, and then we put that over y marginal distribution, which we just found when y is 3/4. 3/2 minus 3/4 is just 3/4. Yeah. Okay. Thus, this would equal negative 4/3 x plus 5/3. Okay, any questions about any of that we just covered? That's all, yes.
You can point at things and say what they're meaning.
This is the marginal distribution of y. This is the conditional distribution of x when y is 3/4. This is our CDF for this joint distribution. This is a table.
Are you taking 4/3 and multiplying by each of those?
Yeah,
So
so
you're getting 5/3 and then.
yeah. I just flipped it like that. Exactly. Okay. So that is all the things about Jdfs. And in fact, let's do something crazy.
This might be really annoying, but what I struggle with is is like applying those conditional things to like a conditional mean or a conditional standard deviation. Like, yeah, mean of x when y equals 3/4.
Yeah.
So,
So that is actually pretty easy. We'll go over that later.
okay.
But essentially, like, you just take your distribution and you just take your expected x for that distribution. So your expected x when y is 3/4. You take your conditional distribution when y is 3/4 for x, and then you just take the expected value of that. And we will go over that later.
Okay.
You have a question, Joe?
So to find the marginal distribution of y, don't you differentiate with respect to x? Or is it the when we use the integral with respect to x?
Yeah. We took the integral with respect to x. And so we integrated over all of our x's, and then we got,
Oh, okay.
yeah. Okay. So these are those first functions that we talked about, except our bounds for x were 1 and 3. So that's what the PDF looked like. And then the CDF looked like that. That's what we always do. PDF, CDF going all the way to 1. Pretty simple stuff, yeah? Okay, so with two variables, we find ourselves in kind of a 3D lane. So what did we have? We have negative x minus y plus 2. And let's see, they were between 0 and 1. Okay, so that is your PDF right there. Okay, you see for any value of x and y, this is what's going on. X and y are both going from 0 to 1. And your PDF looks like this.
Like?
It's a little weird. It's what we think it's going to be than 2D. But that is what it looks like. And so, if you integrate over this entire thing, that the entire area under this lane, plane, I guess, is going to be 1. That's what it's all going to equal out to. And I think we got negative x squared y minus y squared x over 2 plus 2xy. And then we have some bounds here. X less than 1. Then we less than y less than 1. So our CDF starts at 0, and then for any value of x and y, if all the different values, it will take on any range of numbers until it peaks out at 1 right there. Okay, so that is what a CDF looks like. All right. Now we found a marginal distribution for y, which was just 3/2 minus y. Okay, so notice with your marginal distribution for y, you have removed x from the equation. X can now be anything, literally anything in the universe, and doesn't matter. And it's kind of like you've gone back to 2D land, and this is your marginal distribution for y. It is a two-dimensional line. You guys seeing that line right there? Yeah. So that's the marginal distribution of y. Okay, you have now taken x out. Yes.
What does marginal distribution of y mean contextually? Is there a contextual answer to that?
That's an excellent question. That was an excellent question. I think ChatGPT would probably give a better answer than me. Okay. But basically, removing x from the equation, this still, if you integrate it, I don't know if it's just if you under this entire curve, or line, I guess, that would still equal 1. So basically, you created a new PDF where, like, it doesn't matter what x is. You're just looking in terms of y. Okay. That's cool. So that's the best explanation I can come up with. The other thing we did was we had a conditional distribution where negative 4/3 x minus 5/3. Okay. Negative 4/3 x minus 5/3? Plus 5/3. Plus 5/3. Okay, okay, so this is a conditional distribution where we've set y to be 3/4, and when y is 3/4, this is your PDF for x. Again, we flatten the graph, remove that variable, and now we have new thing. I honestly don't know if any of that helps you guys out at all or is interesting, but you've now seen some funny graphs. So there we go. Now, let's see. All right, I'm now going to erase all of this. Okay, so let's talk about expected values. So you are familiar in discrete land that the expected value of x equals, this is what you did. This is what you guys have been doing for like a really long time. You would take all of your individual x's and multiply them by the probability of observing that particular x. Right? You guys with me on that one? Okay. So with a continuous function, expected value of x, you're going to integrate over the bounds of x, and then you're going to multiply it by your function. Okay? Do you see how those are the same thing? Right? You're summing over all of your possible x's and multiplying it by your function, by your PDF. Okay? So expected value.
So it's the same thing as variance.
In discrete land, yes, because you can look at any value of your function, and that is your probability for x. When you're in continuous land, it works a little bit different because the probability at any given point is 0. So you have to integrate under it to get your probability. But here, yeah, it's the same thing. Right? Okay, so let's go on to variance. Okay, the variance of x, you guys will remember, is expected x squared minus expected x squared. Okay? The variance of x in continuous land is, who would have guessed it, expected x squared minus expected x, sorry, I should have put f of x right here, squared. Notice how nothing has changed. Okay, are we seeing a pattern here? We're taking the covariance of x and y. We have your expected xy minus expected x, expected y. All right, covariance of xy with continuous function. You have your expected xy minus expected, make sure I'm doing this right, minus expected x, expected y. Okay. Covariance. Big value, variance, covariance. You've done correlation, which is sigma xy over sigma x, sigma y. And we just covered, how to get the covariance of xy and how to get, your standard deviation for x and y. You just get your variance and you would root that. Okay, yes?
On the covariance, are you using the joint distribution function?
Mm-hmm. Oh, so sorry. I have made a grave mistake. Yes, this is the joint distribution function. So expected xy is going to be your expected joint distribution function, xy times the probability, or the function of the probability of observing each x and y.
And then, so like if in the problem they only give you the joint, would you then use the marginal
Yep.
distributions for?
Yep, these are marginal distributions right here.
Okay.
For x and y. Okay, perfect. So that's great. We know that nothing has changed in this class at all between continuous and discrete. If you know continuous, if you know discrete formulas, you know continuous formulas. Okay, so that is that stuff. Can I erase this or? Yes, still, yes.
Could you rewrite this covariance one just a little bigger?
So sorry. Yes. The covariance of x and y equals I probably wrote it wrong the first time, to be honest.
Input y.
Yes, thank you so much. Those are hard to write, dang. Okay. Does it make sense?
No.
Should I leave that up or
You're good.
erase it? Okay, you're good. Any questions about expected value, variance, covariance, correlation, all that stuff? All right, we're good. I'm going to talk about a little bit about the different distribution you guys have seen. The first one is the most interesting and complex of them all. This is, you would see it, your function of x, if x is in some bounds, then it's some number, 0.5. Otherwise it's 0. This function would look like that.
Oh, that's the.
That is a uniform distribution. Very interesting. Okay, cool. So we have the uniform distribution. Oh, by the way, what would be the CDF of this distribution?
Straight line.
Yes, it would be a straight line. What would be the exact function? Can you tell me?
I think it's x minus a or b minus a. Something from 0 to 1, and from 1 to 3 it starts at 0 and goes to 1.
I think that might be one of the, like a shortcut rule for one of the values, like expected value or something.
So whatever starts at 1 and goes to 3 and starts at 0 on the y and goes to 1 on the y.
Okay, so you're saying it looks like that.
Yeah.
All right, I agree. Does anyone have a function that can plug in?
Y.
All right, let's integrate it. If I integrate this, I get 0.5x. Plugging in from 1 to 3, that's going to be, let's see, or no, sorry, from 1 to x. From 1 to x, it's going to be 0.5x minus 0.5. So 0.5x minus 0.5 is my CDF.
Yes.
Looks like it corresponds to that line right there. Okay, awesome. So that is the uniform distribution. You guys have also seen the normal distribution, which looks a lot like that. Okay, you'll have some mean right there. Yeah, I'll do that. Okay, you would say x is normally distributed with some mean mu and variance sigma squared. And if this happened to be 0, and your variance was 1, that's what we would call a standard normal distribution. Okay. Special normal distribution where the mean is 0 and the variance is 1. That's standard normal. All right. So that's also called the z distribution. So if you're ever given a Z table, which you will be on your exam, then you know that is the normal distribution. You've been given the normal distribution. Okay. So a kind of related distribution is the T distribution, kind of an interesting one. T distribution depends on, it's called degrees of freedom, which for a T distribution means your sample size minus 1. That's your degrees of freedom. A T distribution at really small sample sizes looks like that. If I were to increase my sample size, my T distribution would look like that. Bigger sample size, it would look like that. And if my sample size were like 30, then at that point, my T distribution would be indistinguishable from the Z distribution, like really, really small values. So essentially, at like sample size over 30, like the T distribution basically is a normal distribution. So that's the T distribution, very, very cool distribution right there. You also got a distribution called the chi-squared. The chi-squared distribution with really small sample sizes, it also depends on degrees of freedom. You say this is T distributed with some degrees of freedom. Chi-squared distribution for small sample sizes looks like that. As your sample size gets bigger, it looks like that, it looks like that, and it looks like that, and eventually the chi-squared also actually becomes very normal. But that's, we're talking an n of like 100 for that one. Like that takes a while. So you would say that X is chi-squared distributed with some degrees of freedom as well. Okay, so that is chi-squared distribution. Those are all very interesting things. Yeah. So this concept of a T distribution, with a large enough sample size being about normal and chi-squared being more normal, like those are special to those distributions. That's actually a separate concept from the central limit theorem. What the central limit theorem says is that, let's say I were to take, a lot of, it's a good example of this. Say I'm going into society and I'm sampling all these people. I do this survey or something and collect all these numbers, and I don't know what the distribution is. It's probably not normal, probably not T, probably not chi-squared. It follows some distribution, I don't know. But if I sample tons and tons and tons of times, if I keep doing that over and over and over, I'm going to keep getting some sample mean X bar every time. Maybe it's 70, and then maybe if I sample again, it's like 54, and maybe if I sample again, it's like 61, right? If I keep doing this over and over and over, what the central limit theorem says is that the distribution of these sample means that I get is going to be normal. Okay? That is what the central limit theorem says. If I sample over and over and over, the distribution of those sample means is normal, no matter what the underlying distribution is. Okay? That's the central limit theorem. And I know by another rule that actually the middle of this distribution, the mean, is going to be the true population mean. In other words, if I sample more and more and more, those will be centered around the true mean. That's called the law of large numbers. Okay? Separate concepts. Law of large numbers says that all of these are going to be centered around the true mean. The central limit theorem says that they will be normally distributed. Those are concepts that may come up on your exam.
Law of large numbers, one more time, please.
Law of large numbers says if I sample over and over and over and over, all of these samples will be clustered around the true mean. I might get one here, and then here, and then here, and then here, and then here, and here, 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 but the center is going to be the true population.
And why is that different from the central limit theorem? Because,
Well, that says nothing about the distribution. That's just talking about the center.
okay. So the law of large numbers doesn't say anything about really the variance is what Because the standard or central limit theorem would say that it'll have this mean and this variance because it'll be standard, right? It'll eventually be a standard distribution.
That's the central limit theorem.
Right.
It's not standard, because standard is a special name for when the mean is 0 and the variance is 1, but it'll be normal.
So the central limit theorem doesn't necessarily say though that the true mean, like it doesn't specify that the mean that the normal distribution that we're getting from the sample means, the mean of that is close to the true mean of the population.
Correct.
That's only the large numbers.
Yeah. We call this concept where your mean is the true mean, we call that unbiasedness. And that's actually really important in econometrics, because sometimes you will be sampling or conducting a survey, and your survey will be biased. Like your samples are going to converge around something that's not your true mean, which is a problem. Like it could still be normally distributed, but the fact is that like that's not the true mean. So you're going to have a biased sample or a biased estimator for your sample. Okay, cool. Distributions. You guys also have a discrete distribution in your continuous stuff, which I don't get, but it's a Bernoulli distribution. 0, 1. That's what a Bernoulli distribution looks like. Pretty simple. Discrete distribution right there. Yes.
On the test, are we gonna do we have to bring our own little table things, or are they gonna
No. They won't give you tables. That would be hard. That would be hardcore. Yeah. No, you'll have those tables supplied to you. Yeah, yeah. If you, yeah, do you guys all know how to read those tables? You want to go over how to read them? Okay. Yeah, we can go over that. Cool. The thing that I probably won't go over is stata commands. Honestly,
Yeah, we want
He also recorded it.
Yeah, that's all we did.
I don't know why we did that.
I agree.
Parents
It's
still
like 50
slide,
minutes
Yeah.
of stata commands.
yeah, if it were me, honestly, like, I would just take each of those commands, honestly, and just put them in the chat. That's what I did, yeah.
Yeah, he like literally went through every single command and described it.
We spent 15 minutes talking about why it had to be on the test.
That was so funny.
Okay, cool. Z-table. This is Z-table. Every Z-table comes with a nice rule that tells you how to read it. It says here's your Z right here, and all of this area shaded under is what it's going to give you as probability. Okay?
So if it's like 0.2, then it'll be from the left to the Z point. That's 20% of the probability.
On this, yeah, on this table,
Yeah.
it would be so for example, if I wanted to be 28th percentile, if I wanted this area to be 0.2, and I would find 0.2 in here somewhere. It's about right there, okay? So the 20th percentile is about negative 0.84. Okay, this is for Z table, this is the first number, this is the second digit, 0.84. So when Z is equal to 0.84,
Can you slow down a little bit?
running that back?
Yeah.
Isn't it?
I think a lot of
I
people missed
thought,
that.
yeah, I think it's right.
This is for the standard normal,
yeah.
Oh, yeah, so I was thinking about teachers.
And how many of you guys can see this?
Yeah, now, yeah.
Can you see this? Okay. Okay. So, what? Oh, that's a horrible normal distribution. Whatever. Okay. The point is, when z is negative 0.84, then this is 0.2. Okay. So, I did that because I wanted the 20th percentile. This area is 0.2. I went down here. I found 0.2, which is about negative 0.84. And that's what z is right there. Yes.
So, say we're taking the test, right? We're shown that graph and it says we want to know the 20th percentile. So we just look at the paper, at the table, and figure out what is closest to the 20th percentile.
Yeah, I mean, you could like, make some, say like, oh, I think it's like 0.838 or like something like that. Doesn't matter.
So if you get close to it, it should be okay.
Yeah, I mean, as long as it's on the table.
As long as it's on the table.
Yeah. Get as close to it as the table can.
So don't put negative 0.838.
Well, like that would be close,
Okay.
but like 0.8.
Okay. Yeah. Okay.
Okay. So if
The other way around.
If I were getting, so a normal distribution, again, has some mean, but like if it's not standard normal, this mean might be like 34. So 34 is not on my table, okay? So the way that we standardize those statistics is we take our observed x, what we're interested in, we subtract what our actual mean is, and we put it over the standard deviation of our normal distribution. This, you guys should all know. So x minus mu over theta, or sigma, will give me something in terms of the standard normal distribution. So let's say I had some normal distribution, the mean was 34, the variance was 9, and I was interested in...
Wait, over variance or standard deviation?
Variance is 9. This is the standard deviation.
Okay.
Yeah. So, and I was interested in finding the probability that that x is less than 37. Okay, so I have a normal distribution, my mean is 34. I want to find the probability x is less than 37. The way I would do that is I would take the x I'm interested in, I would subtract my mean, put it over my standard deviation, which is root 9, which is 3, okay? And that would give me a z in terms of my standard normal distribution, where the mean is 0 and the variance is 1. It would give me this number right here, okay? So if I did 37 minus 34 over 3, what is that? It's 1, right? So magic. All right. So this particular case, like I would look for 1 in the z table. Okay. So, and in this particular z table, you can see that they're all negative. And then it also gives you, let's look at this one. So this one I could find, where is z1? It's 1 right here, 1.00. And at 1.00, that is 0.8413. That is the probability that x is below 37. Okay, we good on the z? Now we can go back to a detail. All right, so the detail is in terms of degrees of freedom. All right, so I need to know my degrees of freedom, which is my sample size minus 1. And let's say I had some t distribution, and let's say like the same thing, except, oops, like I'm not in standard normal land, right? I have a t-distribution. So actually, does variance matter for t-distribution? Probably not. Yeah? No. That doesn't. Okay.
So your degrees of freedom is your sample size minus 1?
Yeah, so if my sample size was 10, my degrees of freedom would be 9. Okay, so in a t-table, this kind of has like confidence levels on it, so it's a little different. But this would be the cumulative probability. That's what it says right here. So the cumulative probability right here is 50%. So,
No wonder you guys get along so well.
There's no way that table is correct. If that whole column is 0,
It's a little lazy. You can check it.
this is. Okay. This is going to be the cumulative probability. So if the cumulative probability of the t distribution is 50% or 0.5, then that is just going to put us at 0 right there. That's your t value.
Yeah.
Okay. The cumulative probability is 75%, 0.7, 80%, 0.8, 85%, 1.1. So you see how t is getting farther and farther to the right as we increase our cumulative probability. So it's a little different to read than the z table. Okay, hold on. So this column is saying this is cumulative probability, which is like a CDF.
Ours doesn't have that.
Does your table look different?
It does have 1 tail, 2 tail, and confidence level, I think.
No, it doesn't.
it has confidence level at the top and then the 1 tail and 2 tail at the bottom.
Cumulative.
So one on the right. So just disregard the t notation of the cumulative probability.
Oh, okay. So on your t table, wait, is this your
Well, it says that the confidence level you
Confidence levels at the top and
minus
then
the opposite.
1 tail and 2 tail probability at the bottom.
Yes, you just calculate the cumulative probability by yourself.
okay? So on your guys' t table, the one-sided, it actually says right here, the one-sided is what's shaded to the right of this t, right? Yeah.
Yeah.
Okay, so what's shaded to the right of that t is your one-sided probability. Your two-sided probability would be actually both of those areas summed together. So what's for the right of the right t and what's for the left of the negative t? That would be your two-sided.
Yes.
So your t table looks different. But does everyone get how to read that?
So what exactly do the numbers in the middle mean? Like, what do they
Yeah.
correspond to?
Like, just draw the picture.
These are probably, so you have, okay, these are one tail. Let's use these ones out here. So you guys have a one-sided and two-sided. Okay, so if your one tail probability right here,
It's 50%. Then you have nothing.
so to the right of your t is 50%. Okay, we're talking about reading your t table. So that's 50%, then your t would be 0. If your one tail probability was 25%.
What do you mean t will be 0? Like the actual number right there?
Yeah, this is your t value. That's your, it's
Oh, I see. Okay.
kind of like a standard normal.
Yeah. Okay.
So if your probability you're looking for is 25%, okay, if that's your one tail probability is 25% with 9 degrees of freedom, and your t will be
You have a confidence level of 65. So you're 95th. Wait, no.
0.70.
You're the 105th percentile? How does that work?
It'll be.
What's the question, Marco?
So in this thing, he was talking about, he was calculating it, originally he did it based off confidence level. And he's like, okay, if you're in the 90th percentile, that means that you're at the 80% confidence level. But like, if you're in the 95th confidence level, does that mean that you're, oh, never mind, okay. I'm understanding,
Okay.
I think.
So, but it's the same, 50% of the observations fall
Yeah.
in that area. Right?
Well, no, it's 50% is on the one side, and then you have to match that with the other 50%.
No, that makes sense.
Have you got ever confidence intervals?
And I guess.
Not really.
Okay.
Because it'd be like.
If you don't know what a confidence interval is, I think confidence interval is just treat it like a Z table and read the one-sided probability. Alright. Good. Notice that when Z is really high, this is actually going to be the same as your standard normal distribution. So one tail, if your probability is 25%, you see that this number with really high degrees of freedom is going to be 0.675. Okay? If we had our Z table up still, then let's see. Then if we wanted this area to be 25%, 0.25, then we would find because I'm going one side and not the other side.
Yeah. You'd be looking for 0.7.
Yeah, so for
That's a nice little revision.
yeah, this is actually what we're looking for.
Yeah, a couple of years ago was this, but that was like,
Oh my God.
that's nice to have that though. This is really nice.
I found 0.025. But same concept. Okay, let's say I was looking for 0.025. Okay. 0.025 is negative 1.96. And right here we see that 0.025, one-tailed with really high degrees of freedom is 1.96. Okay, you see how it's the same as the Z distribution when we get really high degrees of freedom.
Is degree of freedom always going to be given? They're like, hey, this is the degrees of freedom, whatever.
Yeah, they might give you your sample size. And if they give you your sample size, subtract 1. But if they say this, X is T distributed 49, then your degrees of freedom is 49. Okay. T table, Z table. We'll go over chi-square really quick. Here's a chi-square table. It tells you that what's shaded to the right of your chi-square value is your probability. So if you have 20 degrees of freedom in your chi-square, and you want this probability to be 0.995, then this is to the right. Okay, this would be 7.434. If you want the probability to be really, really small, then you're getting up to about 40 for your value of chi-square. So pretty similar value, that's how you read chi-square table.
So we just start from the right?
Yeah, for this table, it tells you that here's your number, and the probability is everything, shaded to the right of that number.
So it's not the 90th percentile, then we need to look at the 10th.
Yes, this one right here will give you your 90th percentile. Yeah. Does that make sense? 90th percentile is what is 10% to the right. If you're looking at the
Sometimes you go to the left. But the chi-square gives you the area shaded to the right.
Okay.
The exit. That's why my
Actually, I have at this point covered the material that you guys have covered in class thus far guys went over that pretty comprehensive? Okay. Are there any questions at all that you guys have? Just in general. Yeah. Yep. We can absolutely do that. So I bet there's one on this.
You should say. So basically.
Perfect. Let's go with this problem. Consider two random variables x and y with one PDF guess. The first question is find k so that this is a valid joint PDF. So notice that k is in bounds. What would you do to find out if this is a valid joint PDF?
I would probably integrate it, and then I'd set up. I'm trying to think through my mind. I'd set up my integrals, and basically I'd figure out the value of k, so that when I solve the integrals, it'll equal to 1 total. When you minus it from 0, plain 0. If that makes sense. But maybe that's not right.
Yep. I mean, I don't know if this is exactly what you said, but basically, yeah, you're going to take that double integral over the bounds of x and y, and the bounds of x and y are what?
0 to k.
0 to k, right? So you're going to take your double integral from 0 to k of your function to 81 x squared y. All right, take that, the x dy. Yeah, and so you're going to take that double integral from 0 to k. You're integrating over the entire thing, and that should equal 1. And plug in some algebra after that, and whatever makes that equal 1, that is, you solve for k. All right, makes sense?
I have one question, because it might make it easier. Marginal density is also equal to 1, right? Marginal density of x and marginal density of y.
Yes.
So you just kind of solve it separately.
Any density function, probability density function, marginal density function, like the integral of each of those is going to add up to 1. Otherwise, it's not valid. Yes. Okay, so that's pretty straightforward. Find the marginal density functions for x and y. So how would you do that? So actually at this point you will have solved for k, so you'll have so you'll have what your bounds actually are. K is not actually in your function here. So you would integrate from 0 to x of what your function was to get the marginal density for y, and you would integrate from 0 to y to get your marginal density for x. Okay, here's your board. Find the expected value of x given y equals 1. Okay, so let's break this into two parts. First off, the marginal density for x when y equals 1, how are we going to find that? What's the formula for that bad boy?
Intersect of the joint probability when y equals 1 over the marginal density when y equals 1.
Okay, so we're going to plug into our joint function x and y at 1, and we're going to put it over the marginal for y when y is 1. Okay, so by doing that, let's just, we'd have to solve for k. Do you guys want to go through this whole problem? Or do you just want to go over the concept? Okay, so you would solve for k. At this point, you would have your marginal distribution, your marginal function for y. Okay, so really at this point, you just plug this into your joint function when y is 1. You plug y equals 1 into your marginal function for y, and then you're going to get some function over here in terms of x. And then when you have this conditional function, you're going to take the expected value of that function.
Of the function that you solve for x.
Yes, this function, the expected value of that, let's call this function, special function x conditional, right? Because that's not confusing notation if you're in 3D, right? So that's going to be equal to your bounds for x. You're integrating over that. You have your x times. Sorry, that's bad notation. Okay, this function we're going to call the conditional function of x. I like that better. Okay, so that is what you would do. That will give you your expected value for x when y equals 1.
So it really is just the same as when you're calculating expected value or any other like variance or whatever. It's just that instead of the normal f of x, it's the conditional f of x.
Mm-hmm. Yep, this f of x is going to be this. Exactly the same. Okay, any other questions?
How do you find independence? That's the next part, but I feel like he normally was just like,
Okay, you guys taught 2 definitions of independence. What are those definitions?
probability of each other, like probability of x and probability of y is equals, like, we're given y is just the probability of x.
Okay. Equals.
Just,
Is that right?
yeah.
Is that right?
Yeah, I kind of combined 2 and then I have to understand, and then I did that.
The other definition is probability of A given B equals
Probability of x.
That's just probability of A. So either of these definitions will work. Okay, so if you have the marginal density functions for x and y, and you multiply them, and it was the same as putting that value in your joint density function, then they would be independent. Also, if you had a conditional function, and that was the same as putting it into a marginal function, then they would be independent. Does that answer your question? Slow head nod.
I'll work it through and then it'll be good. But in this one, you would just do the probability that you find for the marginal density function of x, and then see that is equal to the function you find of x.
Yeah. Just plug the same numbers into your direct function, and your marginal functions and then find the other and see if it's the same. Other question? No other question? Okay. Perfect. Anything else specific you guys want to go over? Yeah.
Could we do question 5 from the same test? I'm looking ahead and it looks difficult.
Question 5. Oh, this is, thank you for bringing this up. This is something I didn't cover, but that will annoyingly pop on the test for probably no reason. But, okay, this is just a random rule that you guys should just know, and you might see it or might not, but if you see it, it's what it means, okay? This right here, this z over root w type thing.
Oh, this is what we did in class.
Yeah.
This is P distributed with degrees of freedom 100. Okay. I actually make sure I'm saying that right. Yeah. So this right here. So if you see this notation, like, just know that if you see any z over some chi distributed variable, over its degrees of freedom, I know this like such a random thing, but like this is such a unique instance that I feel like it would pop out to you guys if you see it on a test. So this, just like get rid of the z and w and root w and replace it with t. Okay, so kill that z and root w, replace it with t, and that's your degrees of freedom.
Does z always signify a standardized normal distribution? Like, what if z had been, like mean of 2 and variance of 3? Like, would that rule still hold? Z over that chi-square distribution kind of thing?
Typically, it's used for standard normal. I mean, technically, I could
Standardize
tell
it?
you that Z was chi-square distributed, but that would generally be bad practice. Like we tend to reserve the letter Z. Yeah, it says right there. And I don't think you just throw.
But like if Z hadn't been 0 and 1, would that rule still hold up? If that makes sense.
That's a good question, actually.
Maybe I don't need to know then. We'll just.
Yeah, I think if you have a question like this, then like.
Class you first started with Z state.
Okay, so yes.
I'm assuming yes.
So this is like a very unique situation where you have a standard normal Z over a squared over C. Yeah, very good question. Okay, you just make it a T distributed variable. Okay, actually something else for there. Let me actually go over this. This is a good problem. Okay, F. What do you guys think of this? If f of x, y is the joint density function for random variables x and y, where this is the domain for x and y, 0, 0, 0, 1, then true or false, this is the correlation between x and y.
Oh my gosh.
That's a very quick false. Have you done this? Why was it false?
It's missing like the square roots and
Yes. Wow, that was incredibly quick. Yes.
Wait, what?
That's making it quick. Okay, for those of you, what's your name? Amelia. For those of you that don't think as fast as Amelia, so we know that the correlation coefficient is your sigma xy over sigma x sigma y. Okay. If you were to plug these in for continuous land, we talked about how to get the covariance of x and y. So you guys basically would make sure that the covariance for x and y is correct on the top, and there's actually there's plenty of places that could be wrong. So you gotta make sure that's really correct. But you guys remember going over this. So could you guys all reproduce this covariance?
What's studying?
No? Could you reproduce?
Oh, that's like the simplified rule of the variance of x, y minus.
Yeah, could you reproduce that?
Yeah, I think so, yeah.
Okay, and could you reproduce that? If you can reproduce this, and you can reproduce that, then you can reproduce that top line. I'll just plug in some things.
It also doesn't seem like
Yes, but
You were on the bottom?
it's a good
yeah. So the time y is from 0 to 1, and
Oh, yeah.
Oh yeah, you're totally right.
except it's like very
Yeah. Weird. So, two errors. One, he doesn't have the right bounds for y, and two, he doesn't have the square roots on these variances. These are variances. Right
Like
here.
if there was a square root over the two,
Yeah.
that the two.
So you would need those to be rooted.
But
Yeah.
sounds like an example, I'd be like, well, what if
I like
That would suck.
this right now is very
Yeah, okay.
Yeah.
We have a few minutes. Any other things that you guys don't feel confident on and want some more practice?
square.
This is okay.
But if it highlighted them.
All right. How about we go through one problem and we'll call it.
Square exceed, yeah.
All right.
That
What
would be
is a
correct.
given problem? I think
But
this is
you-
good. Let's go to problem two. Okay.
It's not square.
Would somebody like to come up and just go give
Steve, which
problems?
practice exam is this?
Oh shoot.
Was it two?
Yeah.
Sorry. Practice exam.
I just didn't realize that. That's fine. I think you have a problem too. Who wants to come up and try this?
What is the problem?
So x is a continuous random variable. It's going to
I know, yeah. You can't tell this, but I can choose.
It's between 0 and 1. So this is the PDF for x. If x is in 0, 1.
And Q as well, feel like
And in Desmos, we have the probability x is less than 0.5. Who wants to come do it?
I could try it.
Let's
Mostly
see.
because I need the help, so.
do it.
Maybe, maybe
I
it'll help.
rather enjoy what I'm doing.
Maybe it'll help to
Come
try
on,
it.
let's do it. What's the probability x is less than 0.5? It's actually more than 0.5.
Wait, it's more? Oh.
I'm like, how can I focus in the test instead of in B1?
I do have one quick question. Could you, can you solve this with just the marginal density of x?
Yeah, as opposed to not taking the CDF.
Yeah, could you solve with just the marginal density of x?
You can, you have to do some work, but.
So maybe do the CDF instead. Maybe let's do that. So I first integrate it. And I would personally distribute it out. So then I'd get a 1/2 x to the 4th plus 1/2 x to the 3rd. And then well, I was thinking this was a joint. This is only a single. This doesn't have y in it. Oh no, this isn't bad. Then I'd solve from 1 to 0. Plugging in 1 will just get you 1/2 plus 1/2. Minus 0. But let me think of what that. I'm so used to doing x and y. That just shows that it's a legit CDF. So then I just plug in, I think, 0.5 into here. Actually, that wasn't necessary.
Yeah, I actually don't know how you do this with the CDF because it's more than 0.5.
So you just integrate those words. Don't you just do 0.5 to 1?
Yeah.
Can you just put 0.5 into here?
Yeah, I think.
Yeah. Okay. What's 0.5 cubed? I mean, not cubed to the 4th. I don't know that answer.
Wait. Oh, you just do 1/2.
Yeah, that's how it.
Do I need to, would I need to plug in this x to here?
So here's what I'm saying. Like, if you have a CDF, like your CDF is going to follow like some value to 1, right? But like the probability x is more than 0.5. Like this is going to give you the probability x is less than 0.5.
Well, yeah, then I just take that minus 1 from it.
Oh yeah.
That's what I was planning.
Yeah. Okay. All right. Do that.
So I did plug in 0.5 to here though, right?
Yes.
So 0.5 to the 4th.
Yeah. Do it with 1/2. So 1/2 to the 4th is 1/16.
Why would I not do it? Oh, I see. 1/16 times 1/12. I mean 1/2. So that's 1/32 plus. That would be 1/8, 1/16. So this is 3/32. 1 minus that. That's the answer.
And that is.
Hopefully the answer.
29/32. Yep. Sweet. You got it. You can also instead of getting the CDF first, you could integrate from 0.5 to the highest bound of x, which is 1. And that integration would give you the same answer. Yeah. Question?
That's what I said.
Okay. Okay, the next question actually is, what is the CDF of x? So if you did find that in the first question, then you did the second question. So.
And the CDF is the 1/2 x to the 4th plus 1/2 x to the 3rd.
Yeah, that's the CDF. Yeah, right there. And then the last question is, okay, here's the last question. Let y equal 1 over x. Find the expected value of y and the variance of y. Okay, so this will be the last question we do. Who wants to come up and do this?
I gotta mix some words.
Who's got it? Amelia, you got it? Oh,
I can do it.
yes. Let's go. What's your name?
Tyler?
Tyler? Okay. Let's see it.
Okay.
You can erase this problem here.
So it's just finding E of y and B of y, right?
Mhm.
Okay. Alrighty. What is it? Maybe, I don't know. 17 over 12. That would be
17/12?
what I would guess. Not sure. That's for E of y only, though, not B of y, but.
Yep, 17/12 is expected y.
Solid. Cool.
Yeah, do you want to explain really quickly?
Yes, so I just took this, right? And all you do is, instead of E of x where you multiply by x, because y is 1 over x, you just multiply 1 over x times the original function, and then you just, distribute it out, take the basic integral, and then, yeah, not too crazy, but.
Does that make sense to everyone? Margot?
I'm reading my eyebrows.
your face is bad.
Well, just because it was expected value of y, but that function, I guess that is.
Right, I'm just substituting the y equals 1 over
Yeah,
x, so.
This y, it's not a variable.
Yeah.
Well, it's just something in terms of x.
Uh-huh.
Like this is the same question as find the expected value of 1 over x.
Yeah, yeah.
And so you're
That makes
just
it a little bit more clear.
plugging in 1 over x right there.
Okay.
Yes. You have a question?
You answered it.
Okay. Okay, and then the variance of x. We'll find the variance of, or y. We'll find the variance of y for us. It's like, yes, let's go. Let's go.
I erased a little bit.
Yeah.
Or maybe I'll work with that.
It's Tanner, right?
That's right. That's 17 over 12?
Yeah, 17,
The
12.
one that's really tight.
Okay. Zero to 1 is that? Not bad. So that will just be 1 times. Yeah, so is it just 2x plus 3 halves from 0 to 1? Did I do that right?
There's a lot of mental math.
So 1 over x is, or 1 over x squared is 1 over x squared times x squared.
Oh, yeah.
That's 1.
You're right.
So you just have that. I do that right. So I think you've got, actually,
Do you still use
Actually, I think
integrate though, or
just
do
do-
that integrate?
7.
Oh, yeah, you didn't.
Oh,
It's just from 0 to
You're
1.
right, I did. Got ahead of myself. So I guess that's just going to be x squared and then 3/4 x, or no, 3
Yeah,
3 halves. And we're going to get just 1 plus 3 halves, I think. So 5 halves is y squared. And then we just got our, that, was it 17 halves?
Yeah, 17, 12.
Oh, 17 plus, okay. So just 5
17
halves, which would be 30 12 minus 17 12 squared. What do we got there? 144. What's 17 squared?
I think it's 289.
Yeah. Yeah. Okay.
What do you want us to do?
That's 360 minus 2. So 71 144. Is that it?
Let's see. It is indeed 71 144. Nice. All right. Anyone have questions about this problem? How do you guys feel about the exam? Going to rockets?
Apparently it's easier than exam one.
Yeah. I sure hope so. Okay. Yes,
Thank you.
no problem.